Hello everyone. Today in this video we will see another example regarding the calculation of the inductance of a three-phase transmission line. Here we are also going to take a case in which we will calculate the voltage drop along the line due to the inductance part. Also we will see that even if the sum of the three-phase currents is zero, that is the neutral current is zero, there can be a voltage drop in the neutral wire if it is there. So let's see what's the example. What we are given in this question is that there is a three-phase 50 Hz transmission line which is 30 km long and it is having four wires, that is R, Y, B, the three phases, and the neutral wire with conductor size 4 by 0. It is also given that this conductor size corresponds to diameter of 1.5 centimeter. Now we are also given that the horizontal spacing between the line or the conductors is 2 meter. That is from phase A to B, the distance is 2 meter. B to C, the distance is 2 meter. And C to the neutral wire, it is also 2 meter. Also, we are given the three-phase currents flowing in the three conductors. You can clearly see that IA plus IB plus IC is equal to 0. That is, the neutral wire is not going to carry any current. So, we will see that the formula which we derived earlier for calculating the flux linkages of a conductor in a group of conductors can be easily used here. Also, we will see that the line is not transposed. That is, the inductance can be different for the every conductor. But here we will only take the case of conductor A, the phase A conductor only. So let's see. First we will calculate the flux linkages. In such kind of questions where we need to find the voltage drop due to the inductance of the conductor, we will first need to calculate the flux linkage of the conductor. And for that, we just have to use the formula which we have already derived in our lecture 25 or the near one lectures. I suggest you that you should visit those lectures so that you can get the grasp of the concept and once again visit this example. Now let's see how to calculate the flux linkage of neutral wire. The formula is very simple. How? It is only 2 into 10 to the power minus 7 Ia natural log the distance between the conductor A and conductor N, that is DAN, which is just 6 meter. Similarly, I will take the second conductor, that is the conductor B, and current in that conductor IB into natural log 1 by the distance between the conductor in which the current is being taken up and the distance between the conductor for which we are calculating the flux linkages. So the distance will be dBn, which is just 4 meter. Now the third conductor is C. So current will be IC natural log 1 by dCn. Now the fourth conductor, for the sake of the completeness of the formula, we will also take the neutral conductor. Although we already know that the current in the neutral is 0. So the fourth conductor we will use IN natural log 1 by R dash. Why R dash? As we have already seen in the formula that here the distance will be DAA, that is the self GMD of the wire. And for a solid conductor, the self GMD is just R dash or R prime. That is 0.7788 into R, the radius of the conductor. This will give us the Weber turns per meter of the conductor. By putting up the values of these figures, I will get that the flux linkage of the neutral conductor is 1.2905 into 10 to the power minus 5 at an angle of minus 43.5 degree. You see, the angle is not that much important here since we can take the zero angle, the reference angle at any point. So we need to first consider only the voltage drop along the length of the line. That is, let us say this is the line of having 30 kilometer length. Let us say here the voltage is Vn1 and at the other point it is Vn2. What we are going to find? We are going to find the voltage drop along the line. So what it will be? Delta Vn is equal to Vn minus 1 Vn1 minus Vn2. So the delta Vn just simply with the voltage drop, that is the voltage drop along the line. This is delta Vn. Now we already know that V is equal to N d phi by dt or N d phi by di into di by dt, just the chain rule. Now what is this? These are the flux linkages only. So d psi by di into di by dt. Now what is this? It is simply the inductance only. So we can clearly see that V is equal to L di by dt. Okay. Further, we will see that V can also be written as V is equal to j omega psi. Why? It is in phasor form. First of all, we should note that it is in complex form, not in time domain form. If we had to write it in time domain, we would have written like this. That is V is equal to d psi by dt. Okay. We already know that from our circuit classes that d by dt can be replaced with j omega while we convert it into the phasor form or the complex form, j omega psi. So from here we have got this formula that the voltage drop due to these flux linkages can be written simply as j omega psi. And since the flux linkages which we have got from the formula are per meter of the length of the conductor, so we need to multiply it with the total length of the line to get the total voltage drop along the length of the line. So putting up the values, we will see that the voltage drop along the neutral wire of the full length of the line is simply 121.63 volt. Now similarly, let us see how to find the voltage drop in the phase A conductor. Similar to the flux linkage of the neutral conductor, we will find the flux linkage of the phase A conductor also. Simply by the same formula, 2 into 10 to the power minus 7, the first conductor and the distance between the phase A conductor and the conductor carrying current. So it is simply R dash when we are calculating the flux linkage of phase A conductor. That is Ia natural log 1 by R prime. R prime is simply the self GMD of the conductor A. Now coming up to the second conductor, current in that conductor and the distance between the phase A conductor and this B conductor, that is natural log 1 by DAB. Now coming up to the third conductor, it will be IC, distance between these two conductors C and A, that is DAC. Now we already know that IN is 0, so I have shown this for the completeness of the formula. So this term will already be 0. Putting up the values, I will get the flux linkage per unit length of the phase A conductor will be 5.459 into 10 to the power minus 5 Weber turn per meter. Now multiplying this with j omega and the length, I will get the total voltage drop along the complete line. You see, there is a voltage drop of 514.5 volt within a length of 30 kilometer only. So you can see that this may create a problem whenever there is a high current along the line. So we will study now later chapters how to reduce this voltage drop, various measures to reduce the inductance of the conductor also, which we already studied here also, that we use bundled conductors, multi-circuit lines, so that the geometric mean radius increases, since the inductance is proportional to, L is proportional to natural log GMD upon GMR. If I increase this or reduce this, the inductance will reduce. So any method which helps us to achieve a lower inductance will help us to reduce this voltage drop along the length of the line. So that's all for this chapter. Now in the next lecture we will start a new chapter, that is the capacitance of the transmission lines. We will also briefly see about the conductance of the transmission line also in the next lecture. If you find my lectures interesting and helpful, then it is requested that you please subscribe and share also my YouTube channel with your friends, so that they can also enjoy the lectures. Now from this video onwards, we have also started a Telegram group for discussion or doubt discussion, which you can subscribe or join using the link which is provided below the video in the details column.